So here we're going to take a look at the graph of this function, and we're going to calculate or estimate the following integral values. And so far, the work that we've done on integrals either requires us to go to the definition of the integral in terms of the limit of a Riemann sum, or to use geometry. And so here we don't actually have a formula for the function, so we can't use the Riemann sum, so we're going to need to use geometry. So take a moment to see what you can determine about what is the integral of this function from 0 to 1 and from 0 to 2. Now you might notice that so the integral is going to be the accumulated signed area between the curve and the x-axis, where if the curve is above the x-axis, we take the positive area, and if the curve is below the x-axis, we subtract the area. So from 0 to 1, we can see that this area here, this area of this triangle, is half of the area of a 1x1 square. Okay, so this integral then is equal to 1/2. Now the area, the integral from 0 to 2 has the same amount of area below the x-axis as it does above the x-axis. So whereas we add the area above the x-axis and we subtract the area below the x-axis, our full integral is going to be 0, because we're going to have a positive 1/2 from that the first half of the interval, and then a negative 1/2 from the second half of the interval. So I want you to actually take a moment to look at what is the integral of this function from 0 up into each integer value. So we want to integrate from 0 to 3, from 0 to 4, 0 to 5, 0 to 6, 0 to 7, and so on. Okay. Hopefully you paused the video and actually thought about this on your own. And so I'm going to go through this, and what we have from 0 to 3, the first from 0 to 2, those two triangles cancel each other out, and then from 2 to 3 we have 1/2 below the x-axis, so the integral is going to be negative 1/2. And then from 3 to 4 we're going to add in a bit above the x-axis, which is going to be positive 1/2. So now from 0 to 4, we have the same amount above the x-axis that we have below the x-axis. So the full integral again is going to be 0. From 4 to 5, we have a trapezoid. So the full area from 0 to 4 is 0, so it's basically just the same as the area from 4 to 5, and that should be 1.5. You can see that there's a 1x1 square plus a triangle, which is half of a 1x1 square. So this is going to be 1.5. Now 5 to 6 is another trapezoid. And so we will have basically a 1x2 rectangle. So there's an area of 2 there, and then another triangle where the area is 1/2. So the total integral, remember from 0 to 4, it's 0. So I'm just counting all of the stuff after that. So it's 1, 3, 4 total square units. Okay. And then from 6 to 7, it's sort of anyone's guess. We don't know exactly what type of curve this last bit is, but you can kind of guess. If I was to do like a left rectangle here, that full rectangle has an area of 3. It's a 1 by 3 rectangle. And it looks like this is a little bit more than 3. So maybe, maybe this part here is, I don't know, 1.7, just taking a guess. So then the total area, again, the first 4 units gets to 0 because the part that's above the x-axis cancels out the part that's below the x-axis. And then we have a total of 4 from 4 to 6, and then a 1.7 guess. So we would guess this to be approximately 5.6 or 5.7. And, you know, maybe you would say that that last bit is, your guess is 1.6. It's just an estimate. So it should be more than 1.5, a little bit. And who knows exactly what it is. All right. Now, I want to take this idea about this. What we've done is we have calculated the integral from 0 to different stopping points. And so we can kind of like ask the question, well, what's the integral from 0 to 1.5? What's the integral from 0 to pi? What is the integral of f from 0 to 4.3? And in this way, we really have a new function, which is the integral so far function. I kind of refer to this as an integral so far function. I'm going to call it g. And our g is really, you know, you take an input value, g of x, and you take an input value, gx, and the value of g is what is the integral of f from 0 to that input value, x. So the way that we do this, so the g takes an input value, x, and it takes the integral from 0 to x of f. And I don't want to call it f of x dx because I'm using the x up here. So I'm going to call it f of t dt. And keeping in mind that that variable that we use in the integral just tells you like what I'm calling the input variable of that function. Okay, so this is the integral so far function. And what I want to do here is I want to see if we can make a graph of the function g. And before, what we did is we calculated what is g of 1, what is g of 2, what is g of 3, okay? So up here, these pieces here, this is g of 1 and g of 2 and g of 3 and so on. So we could actually, we could plot these points, right? G of 1 is 1/2, G of 2 is 0. But I want to think about this kind of organically as this integral so far function by following the graph of f and seeing how that translates into a graph of g. Okay, so and as we're kind of going along, I'm gonna pull out these questions. You know, what do you notice and what do you wonder? And maybe you actually like write down as we're going along what things you notice about this and what things you wonder. All right. So to begin, well, for one thing, what is g of 0? So, I mean, we didn't calculate g of 0. Well, g of 0 is an integral from 0 to 0 of f of t dt. And so if you think about this, if you have an integral that has where you're integrating over an interval of with 0 length, where the beginning and the ending point of the interval are are the same, that integral has to be 0. And you can think about this in terms of area, where there's there's no area under the curve, but you can also go back to the definition of the integral in terms of the limit of the sum, where the sum is of little pieces that look like f of some x value times delta x. And if you look at the definition of the delta x is going to always be 0. So those Riemann sums are every single term in that sum is going to be 0. Regardless, g of 0 is going to be 0. So I start with g of 0 equals 0. And then what I'm doing is I'm looking at the accumulation of signed area as x moves along. So what I have here, I think about what is the area of this function as x goes along, and I'm adding some positive area. So g must be an increasing function here. Okay, and if you think about it, as I am adding more area and more area, I'm actually adding area even like more slowly as I go along, because my height of that triangle, the height of the bit that I'm where I'm adding positive area, is actually decreasing. So my g function is actually increasing, but at a decreasing rate. So my slope is kind of getting less and less. So my g should actually be concave down here. And I get up to where I go where, I go to get to g of 1, which was 1/2, if you recall. And at this point, thinking about what g is doing, this is the accumulation of area. So this is the integral so far. And I say area, but I kind of mean signed area. And after x equals 1, what's going to happen? We're going to start adding negative area, right? And so, or we're going to start subtracting area. So my integral is going to start decreasing, that integral function. So g is going to start decreasing. And as I continue on, I notice that I'm actually adding more negative area at a time as I go along, because the size of my function is getting bigger with respect to the 0. So I'm decreasing, but at an increasing rate. So my function is actually getting steeper. G is getting steeper. And I keep going until I reach where g of 2. And if you recall, g of 2 was 0, because this is where the amount of area above the x-axis equals the amount of area below the x-axis. Okay, and now I keep going, and I'm still adding more negative to my integral. Okay, so my g is still decreasing. But now it's actually decreasing at a decreasing rate. Okay. And I say this decreasing at a decreasing rate, decreasing at an increasing rate. It's getting less steep is what is happening. So the slope is becoming less steep. And then I get to x equals 3, and I notice that remember, g of 3 was -1/2. That's at g of 3. And now I'm going to start adding positive area again. So my g is going to start increasing. And it continues increasing. Remember when we got to 4, we got our g of 4 became 0 again, because I had the same amount of area below the x-axis as I had above the x-axis. And now the integral is going to continue increasing, and it's going to get actually steeper because look, I'm adding more area with every little bit. So this function is getting steeper and steeper and steeper. And we see g of 5 was 1.5. I'm going to mark that here. So it's getting steeper and steeper, meaning the graph is actually concave up. G of 6 was 4. It's going to continue getting steeper as I'm adding more and more positive area here to the integral. And after 6, I continue adding more positive area, but I'm adding kind of less at a time. So the g function is actually going to get slightly less steep. So the function is going to become concave down, and it's going to end up, the 5.7 or whatever is up here, and we don't know where, I don't know where that is because it's off the scale. But this is an approximate picture of what the g function looks like. And I just kind of want to take a moment to write down a couple of the things that we noticed along the way, which is, for one thing, that wherever the function f is positive, the function g is going to be increasing, because as x moves along, as x kind of motors along, I'm going to incrementally add little bits of positive area. Let's say wherever f is positive, g is increasing. And similarly, the parts where f was negative means that I'm going to incrementally subtract some area from the integral. So if f is negative, then g is going to be decreasing. Now, something that you may have kind of noticed along the way too is these local maximum and minimum values of g. And I want you to think about what feature of f that corresponds to. And, what we see here is that, g was increasing and then decreasing, and that's where f switched from having a positive value to a negative value. So I'm going to pop that out for a minute. So wherever f switched from positive to negative, g had a local maximum. And similarly, wherever f switched from negative to positive, f had a local, or sorry, g had a local minimum. And looking at these properties here should make you think of something. Those properties are really the relationship between a function and its derivative. So these are derivative properties. So this is basically telling us that between f and g, one of those functions is the derivative or is related to the derivative of the other function. So I want you to think about which one is which. Between f and g, which looks more like the derivative function of the other? Is f the derivative of g, or is g the derivative of f? So thinking about this, where f is positive, g is increasing, that indicates that f would be the derivative of g. And this is, in fact, the fundamental theorem of calculus, as stated in the first form. Okay, so what this is saying, if you start with a function f, and then you create this integral so far function, g, and the starting point of 0 is arbitrary. You can start at any point. You can start at x equals, at t equals 1 or t equals 5 or whatever. But if you do this integral so far function, the statement is that the derivative of that function is the original function that you started with. So let me write this. The derivative with respect to x of this integral so far function is that original function that you started with. So this is the fundamental theorem of calculus, part 1, and this is really meant to give a little bit of an intuition of how that integral came to be, or sorry, how this relationship came to be, without really proving it in a rigorous manner. Okay. So I do want to actually look at this in a Desmos graph, just to, like, we did this hand drawn, and I think it's a really good practice to work through the stuff in your head to hand draw this integral so far function given a graph of a function. But I want to take a look at this using some technology, because I do actually have a graph of this. So here is the same function. And what I'm going to do is I have, okay, so if I drag this point, basically I am dragging along and calculating the area, the integral so far, where I've encoded negative integral is, the negative areas are encoded in orange and the positive ones are encoded in blue. Okay, and keeping track of the integral, that purple dot is going to be the integral here. So at x equals 1, the integral from 0 to 1 is going to be 1/2. And then as I continue along, my at x equals 2, the integral is going to be 0, because this is, I have the same amount above the x-axis as I have below the x-axis. And then it goes down to 3. And then it goes up to 0. And then it goes up to 1.5. And then it goes up to 4. And then it goes up to 5 point something. Okay. There it is. Oops. So that there is the full trace of the function of the integral so far function. And you can kind of see along the way that the original red function actually does trace out the derivative, or what looks like approximately the derivative of that blue function.